I'm going to talk about statistics. But once again, I'm a surgeon. I'm not a statistician. I want to try to make you understand why these statistics are important. I want to make sure that you understand that statistics are often misused or misinterpreted. And there are a certain amount of traps, easy to understand, really easy. I'm not going to give you any formulas. I'm not going to calculate anything, okay? But there are specific, basic notions that I'm going to go through and try to explain why they are important when you put them into a medical paper. Very famous doctor who said that medicine is a science of uncertainty and an art of probability. This is what statistics are about. Statistics are a way of quantifying the degree of certainty or uncertainty of what we assert, what we put into writing. And actually, it's just talking about the probability of what we're trying to say corresponding to reality. That's all it is. And if you've understood that, you've understood everything you need to know about statistics, except what test to use when. And we'll talk about that a little bit. Understanding of statistics is important for critical appraisal. You cannot read the literature and get the information that you need without a basic understanding of what the statistics are in that paper to understand whether or not you can believe what you're reading. You want to know the strength of the evidence. That's what statistics is about. And you want to be able to distinguish between statistical significance and clinical significance. For those people there's 3 people that have left already. That's okay, not a problem. But for those of you who are there, don't forget to come back the afternoon. If you want to leave, you're not interested, that's okay. But come back for the afternoon session. Clinical research has specific steps in a methodology. You've heard in the beginning, in the types of studies, you have descriptive studies and you have analytic studies. Analytic studies are based on comparisons. You want to know if something is better, well, A is better than B. Okay, it can be a drug, a medical device, an operation, whatever. This is part of your methodology. And you use statistics to have what we call a judgment of signification. Is that observed difference in your experiment, in your study, something that could be considered to be real as opposed to something that could happen just by chance? Further, you want to know whether, if that statistically significant difference is found, is it related to causality? In other words, can I say that A is different from B? I have a p-value that says so, and it is really because there is a real difference, and that difference can be applicable to clinical practice. Once again, causality can be affirmed only by a controlled randomized trial for the reason that I stated before, that the confounding factors that you know about, as well as the confounding factors that you do not know about, are equally distributed by randomization between the 2 groups. Last part of clinical research methodology is the clinical judgment. How can you calculate, how can you evaluate the clinical effect of a statistically significant difference? Very easy. Once again, our objective is to write a scientifically correct manuscript, and that's why statistics are used. And statistics are very easy. It depends on the type of data, whether it's categorical, metric, whether the data is paired or not, whether it's one measurement or two measurements. Two measurements in the same person, the same participant, means you have to use a paired data statistic. Depends on what you're comparing. We'll look at that. It depends on what outcome you're looking at. Are you looking at a prognostic factor? Are you looking at the predictive value of a diagnostic test, of the sensitivity of a specific investigation? Are you looking at survival? Are you looking at cancer-related survival? Are you looking at recurrence-free survival? Are you looking at long-term results of a Nissen fundification? All these factors intervene in the type of statistic that you're going to be using. Basically speaking, three objectives. Either you're going to summarize your measurements and to have some sort of statistical validation of those measurements, or you're going to make estimates or infer a result from the data that you have, or you use statistics to adjust for confounding factors. Everybody following me? I hope. I'm not losing anybody. You'll see it's not going to be very difficult. Let's look at these chapters one by one. You have to understand and remember, it's very easy, that the type of data dictates what statistic you use. You have categorical or metric data. It's very easy. Categorical data are values that can be distinguished from one from another, either because of the name, it's yes or no. This is called nominal data. The patient died or did not die. He bled, he did not bleed. He had a recurrence or not. Or, in the categorical data, ordinal. In other words, values that could be put in a meaningful order, for instance, the VAS score, the visual analog score for pain. Metric data are values that can be put into a meaningful order, but can be measured. Different from categorical, ordinal. And they can be discrete, in other words, each individual value, like a blood group or whatever, or continuous values. In other words, there's intermediate values between 1 and 2, 1.1, 1.2. It's a continuous value. Easy. I haven't lost anybody yet? Good. Don't forget the differences between means and medians. The mode is on there, but no one uses the mode anymore. Let me remind you, just once again, because this is so important and so misused. The mean is the arithmetic center. It's the sum of all values divided by the number of observations. The median is the middle value, or the 50th percentile. If you rank all your values from the least to the greatest, it's the one in the middle. There is probably not one metric misused more often than the mean and the median. And I'm going to try to explain why. Everybody know what a normal distribution is? I'm not going to go into the details. A normal distribution is that there are as many observations that are not close to the mean as there are on one side as there are on the other side. And normally it gives a bell-shaped distribution. This is something very well understood. It looks nice on a graph. But in biology, in human biology, there are actually very few of the parameters that we deal with that have that normal distribution. It's very important because the test that you're going to use for a normal distribution is not the same that you use for a non-parametric or a non-normal distribution. So you have to make sure that what you're dealing with is normal or not normal as far as distribution is concerned. Remember the example that Professor Bene showed you, where there was a mean, I don't remember the number, 1 point something, plus or minus 2. The standard deviation was greater than the mean. How can you have a negative value for that? It's ridiculous. That means that the author did not understand that the value that he was measuring was not normally distributed, and he should have used the median. That's the point I want to make here. Most samples in medicine are not normally distributed. Height, length of operation, duration of operation, duration of hospital stay. You may think so, but it's not true. And even if you have a doubt about it, use the median. You'll never be wrong with the median. Patient age. Everybody uses the mean. First of all, you should not use the mean just because you want to use the mean. If it has something important, it's an information that's important, yeah, okay. But do not forget that it's probably not normally distributed. You should be using a median. The problem is because of the outliers. Remember the normal curve? It means that there are few outliers. Those outliers will change the mean, but will not change the median. In biology, prefer the median. A few words about variability. We want to measure the spread, what we call the spread of data. We usually use for the mean what we call the standard deviation. It's a way of measuring the scatter. It measures a typical distance from the mean of the value you're talking about. It's sensitive to the denominator. It's related to the size of your population. I'm sorry, it's not related to the size of the population. Very important. There's another measure, which is the standard error of the mean, which is used sometimes, which is sensitive to the population. But it does not quantify the scatter. It's only the variability of the mean of the deviation as compared to the mean of the population. Don't use it. Don't calculate it. It's misleading. You also can express the data, especially for medians, with a range. Even the mean. You give the mean, standard deviation, and the range. The lowest value and the highest value. This is information that's important. Or you can express it with the interquartile range. Something like a median, you divide your groups into 3 or the 4, and you use the 2 middle or the 1 middle quartile, as seen here. So, data can be expressed in different ways: categorical, nominal or ordinal, or metric. Some are expressed with the median, some are expressed with a mean, or some are expressed with the median. If ever in doubt about the normal distribution, use the median. And for the spread, the range always goes with the median. Standard deviation always goes with a mean, but you can use a range with a mean, but never use a standard deviation with the median. I don't know how you could calculate it anyhow. And never use a range by itself with a mean. Don't mix them. Once you start with the median, stay with the median. Start with the mean, stay with the mean. Second objective of statistics, to make estimates or inferences from samples. We all deal with samples. We have our population, our case series. We've done it in our hospital, and we want to know if we can apply what we found in that population, in that particular hospital, outside of that hospital. We all think we can do that, but you need statistics to support that. We want to be able to determine the probability, William Osler said that, of what we have observed in that example being the so-called truth in the overall population. This leads me to talk about the two types of errors that I mentioned this morning. Once again, the first type of error, type 1 error, is the false positive error. That means we conclude that there's a difference, but in fact there is none. Everybody knows that definition, everybody understands it, I'm sure. It's that p-value that we use, as a matter of fact. It's the quantification of the probability of what we're saying being false, a positive result being false. That is, we conclude that there's a difference, but in fact there is none. Type 2 error is concluding that there's no difference, but in fact there is one. This is tricky. Type 1 error is easy to understand. Type 2 error is much more difficult. I've alluded to that before. I'm going to insist on it now. Take a look. I'm sure you're going to all understand what a false positive and a false negative is. You go home with that, you'll understand those two types of errors. It leads to what we call power calculation. It's very important for a power calculation. Even if it's not a randomized controlled trial, some cohort studies, in order to come to a conclusion or try to come to a conclusion, you have to have sufficient population, sufficient numbers in the samples. And the sample size is what we call a power calculation. It depends on the expected difference, the delta, in other words, what you expect to prove or to improve. And this effect size, this delta, should be something clinically relevant, either based on retrospective pilot studies that you've done before, or clinical intuition, doesn't matter. And then you enter the type 1 and the type 2 errors. Now, it is well known that if the p-value is greater than that alpha, that type 1 error, usually set by convention at 0.05, we say that the result is not statistically significant. If the p-value is less than that preset value of a type 1 error, it's just something that we have set by convention as 0.05, we talk about something that's significant, statistically significant. Okay, this is all known to everybody. Here's where it gets complicated. The type 2 error, in other words, the false negative result, okay, it's complementary to the power of the study. The power of the study is defined as a probability of finding a statistically significant result if truly that difference exists in the overall population. Don't forget, we're trying to go from a sample to the overall population to infer that what we have found in the sample is indeed the same in the overall population. But here's where it gets complicated. So, if the power were 90%, it's the complement of the beta error, which would be 10% here. It means that there would be a true difference detected in 9 out of 10 cases if the trial were performed a number of times. It's very important, and it's all related to the type 1 and type 2 error. Without power calculations, the reader does not know if you do not find a difference, if that absence of difference is indeed because there is no difference, or just because the population is not big enough. Can I make that again? Power calculations are important so that if you have a negative result, you did not have a statistically significant difference that was found. You want to know whether that is due to a real absence of difference, probable, or just because you didn't have enough patients or population to determine it. That's what a power calculation is about. That's all you have to understand. P-values are the probability of finding a difference at least as large as the one that you've observed. But it assumes that you're talking about what we call the null hypothesis. That means you say the hypothesis says that there is no difference, and you want to prove that there is a difference. If you don't have a null hypothesis, you should not use p-values. Don't use p-values just because you have data and you have it put it into a machine and it calculates the p-value. That has no sense. If you hypothesize that there is no difference between two categories, yes, you can use a p-value. But if there's no sense in hypothesizing that there's no difference between a population A and a population B, don't use a p-value. It has no meaning. The p-value is a benchmark that is by convention, 0.05. But it's a cutoff value. And you can get statistically significant results if you increase the population sufficiently. That's artificial. You want to infer from a sample to the overall population. That's all you want to do with p-values. But once again, when you do not get a significant value out of your p, it does not mean that the null hypothesis is true. It just means that the sample size is not big enough. And you don't know clearly with the p-value if there is or not a difference that you did not detect. Once again, absence of evidence is not evidence of absence. Absence of a significant p-value does not mean that there is not a difference. Okay? Second image to go home with. Let me just talk about something else. P-values are set, as I said, for the false positive, by convention, 0.05. If you test more than one null hypothesis, in other words, you do subgroup analysis, very common, you can't use the 0.05 anymore. Every time you use a statistical test, you increase the risk of a false positive. If I were to do an analysis and I found A is better than B, but then I wanted to do an analysis of the men and women in group A compared to the men and women in group B, I need a 0.025 to test that hypothesis in order to avoid a false positive. Okay? Multiple comparisons, subgroup analysis, for instance, you don't use the same p-value. You cannot use it. Better than p-values is confidence intervals. Our confidence intervals can be used only if the sample is representative of the whole population. Okay, that's easy to understand. Usually we use 95% confidence intervals. Definition is here, the range of values that include the true population in 95% of the cases. They can be computed for means, proportions, ratios, whatever. The problem with p-values, it's a binary, it's yes or no. It doesn't give you any indication of the importance. Yes, 0.00001 is highly significant as compared to 0.04. But it's a little bit approximative. Confidence intervals are much better. These are the terms that we use. As I just said, don't forget the word trend. It should be only used for values of p-values that are between 0.05 and 0.10. Okay? A few words about confounding, and we're finished. Multivariate analysis is used to get rid of the confounding factors, whether it's categorical or, for instance, the time to event outcomes. This is all you have to know. If you have categorical dichotomous outcomes, you have to use a multiple logistic regression analysis. Otherwise, you use the Cox models. That's all you have to know. And make sure your statistician does the work. But you have to be critical about that. And when you read papers, you have to be critical about it as well. Continuous outcomes, you use multiple linear regression analysis. This is it. This is it. I'm not going to go into any more details. I haven't lost anybody yet? Good. We talked about statistical significance. One slide to talk about what is called clinical signification, or number needed to treat. Number needed to treat is the number of patients that have to be treated, or, for instance, a risk factor being avoided to prevent the occurrence of one adverse event. It's simply the inverse of the absolute risk reduction. If I have a study that shows that my risk was 10% before I did a treatment and I reduced it to 5, I have a 5% risk reduction, okay? 0.05. 1 over 0.05 gives me the number of patients I have to treat in order to avoid one adverse event. Two. If that were 2, that's great. That's a very good study. For every 2 patients I treat, I'm going to have a positive result for 1. This is clinically significant. So, statistically, I'm going to finish. We only lost 5 people. Not too bad. Statistical tests depend on what type of outcome you're looking at, whether the data is normal or not, whether it's paired or not, and whether you're talking about univariate metrical analysis or multivariate analysis. Depends on what type of data, continuous, dichotomous, categorical, or time to event, whether it's normal or not. If it's not normal, you have to use non-parametric tests. If you use 1 measurement per sample, it's an unpaired test. 2 measurements for the same person or same animal, paired tests. And these are summarized, I'm almost finished, in 2 papers. One by Curici and Jacks, 2006. The other by Güler, Jacks, 2004. I'm not going to go into details. Just read them. They're easily understood, even for surgeons. Okay? So this is all you have to know about statistics. You don't do them yourself, but you have to know when you read a paper, you have to make sure that your statistician listens to what you say. Okay? Any questions? You have 5 minutes for questions? If not, yeah, sure.
Thank you for the talk. I had one comment about the standard error that you mentioned, the standard error of mean. So there is some value to it because it is the basis for computing confidence intervals. While it's not useful to do descriptive analysis, so it shouldn't be undersell the value of standard error of mean because the confidence intervals and the sample size computations depend on that.
Yes, I agree. But don't use the standard deviation of the mean as a spread for your data. It's important for confidence intervals, but that's something that's done in the calculation. Don't worry about it.